This is 7.4.3, energy stored by a capacitor. Now, we refer to a capacitor being charged by a battery, as we saw in the previous lesson, where we connect the battery across the terminals of a capacitor and we allow it to become charged. Now, what we find with a capacitor is, in the beginning, in its uncharged state, it has no charges accumulated on the plates, and it also has no potential difference across the plates. Once we've connected it, the potential difference gradually rises. As the potential difference rises, the charge stored on the plate also rises. And that's described by the equation Q equals to CV. So as we increase the potential difference, we increase the amount of charge stored on those plates. So if we were to graph this, we've got Q and V, and that increases linearly. And this is described by the equation Q equals to CV. Now, work done that you learnt from AS physics and electricity was Q times by V. In that situation, however, there wasn't a change of Q and a change of V. So if you were to graph that, it would basically just be the area under the graph. In this situation, however, it's not constant. These values are changing. However, it's still going to be the area under the graph. So if we sketch out the area, the energy under that graph is a half QV because it makes the shape of a right angle triangle. Now this raises a question. The question is, that battery is doing work. And the work it's doing is QV. But the energy that's stored in the capacitor is only a half times QV. Where's the other half of the energy gone? So our next endeavor is to describe or explain what's happened to that energy. So our battery is charging capacitor. The battery is providing a potential difference. The potential difference is the work done by the battery per unit charged. So V is a joule per coulomb, the work done per unit charge. And the equation for that, the work done by battery, is W equals to QV. Only half of this work is stored in the capacitor. The other half of that energy is work being done to push those charges onto the capacitor and keep them there. Is work done to push charges onto plate. So I want you to think about it like this. So imagine you've got the capacitor being charged by a battery. Once we've closed the switch, a potential difference starts to build on the capacitor. In the beginning, the only thing pushing charges is the battery onto the capacitor. But the capacitor slowly, or very quickly rather, but it gradually builds up a potential difference as well. And as the capacitor builds more and more potential difference, it's pushing back onto that battery. So for that battery to continue to place charges or push charges onto the plates of the capacitor, it has to do work against the potential difference of the capacitor, which is facing the opposite way. So work is done against that potential difference, and then the remaining potential difference can be used to place those charges on the plate. So as an example, if 6 joules of energy is stored in capacitor, then the battery had to do 12 joules of work.
You know how only half the energy, or only half the work done is on the capacitor. Does that apply to other things like thermistors and LDRs?
No, because we're not charging them up. The capacitor stores charge. The more charge it begins to store, the more it's pushing back. Eventually, it gets to a point where the battery cannot charge it up any further, because their potential differences become equal in the end. They push back equally and work stops being done. But up until that point, some work is done to overcome that potential difference that's pushing back. Yeah? So half of the work that's done is to overcome that potential difference pushing back, and the other half is to store the charges on the plate of a capacitor. Now let's look at deriving the energy equations of a capacitor. So we have a QV graph. If we choose some point on the potential difference and we label that as V. So for example here, if we call that V, and then we increase the potential difference by another amount, and we call that extra amount delta V, we can end up somewhere greater, which is V plus delta V. If we make delta V very small, so we're very, very small, we're going to slide that line V plus delta V closer and closer and closer to the original value V that we've marked. Yeah? Now, if we bring that line very close, such that the separation or the thickness is infinitely small, what would the value of charge be at V and V plus delta V? It'll be the same. If you only increase the voltage by an infinitely small number, you're not really increasing the charge at all. So the values of the charges are the same. So if we add, or adding a small voltage, delta V, will increase the charge stored on capacitor if delta V is infinitely small. And when we say things are infinitely small in mathematics, we stop writing delta V and we now call it dV. Then Q as a function of V is unchanged. For that small strip. Now, if we divided this up into an infinite amount of small strips and we added them all up, we're basically doing a mathematical operation called integration. So the area of each of those strips that are infinitely thin is Q multiplied by the thickness, which is dV. So Q dV. And that's equal to an infinitely small amount of energy. Remember what I said, if you have something that's infinitely small change of something, we call it dE rather than delta E. So our infinitely small change of energy is equal to Q times the infinitely small change in potential difference. We're going to now do that and evaluate that across the entire line. So the integral of dE is equal to the integral of Q dV. Now, if Q was a constant, the integration would be simple. It just becomes QV. But Q is not a constant. Q is a function of potential difference. And that comes from our capacitor equation, Q equals to CV. So if we want to integrate Q, which is a function of V, we have to do it with respect to V. So we're going to substitute, instead of Q, we're going to put CV. So the integral of dE is equal to the integral of Q, which is CV, dV. And if we're evaluating this from V equals to 0 up to some arbitrary value V, we can put our limits in as 0 and V. And so integrating this, if you integrate the infinitely small change in energy, well, that just becomes energy, is equal to CV integrated becomes a half CV squared. And if we were to quickly evaluate the limits, we would have a half CV squared minus 0, so that's just a half CV squared. And that's our energy equation. So what we've done here is we've taken our graph, Q, V. We've divided it up into very, very small strips. And we've added up the area of all these strips. So the total energy is equal to the sum of all areas of strips. Now, we can take our capacitance equation and substitute it again into the energy equation, and we'll get 3 equations out of it. So we've got one here. I gave you one before, but we're going to create that one now. So we know that CV is equal to Q. Here we've got CV squared. So if I take one of the V's and C and I substitute for Q, we get E equals to a half QV. This is the one we've already had. And if I take the V squared, well, we know that Q equals to CV. So V squared equals to Q squared over C squared. If we substitute into there, the C squared will cancel, the squared will cancel out with the C on top. And we'll get E equals to a half Q squared over C. And these are our 3 energy equations. And that's the end of 7.4.3.